Hello grade 10s, in this video we're going to take a look at some electromagnetic radiation past paper exam questions. So let's jump right in. Remember to stay tuned throughout the whole video. I give teacher tips that help you level up your marks. I am a teacher working and living in this country, so I know exactly what they're looking for when they set your papers, when they mark your papers. So let's go.
The first thing that I want to say is that when you do an exam or when you do a test, you will receive a formula sheet or data sheet. Now this sheet has multiple things on it. The one thing that it has on it is something called our physical constants, our table of physical constants. And that is this table over here. Now what this is, and you should know what constants are. Constants mean that they always stay the same. They never change. And for waves, and in particular electromagnetic radiation, the constants that we care about is the speed of light and Planck's constant. So these two constants will be ones that we will use throughout our calculations. They give it to you in every single test and exam. So you don't have to memorize them. Use your formula sheets and look at them and make sure you get them correct. Then the second thing that they give you is obviously your table of formulae. So these will be given to you. You do not have to memorize the formulas. You select the correct formula applicable to the question. You write it down because that gets you a formula mark. You substitute in because that gets you a substitution mark. And you get an answer with a unit that gets you your answer and unit mark. So in this video, we're going to be looking at a variety of different types of past paper questions. We look at multiple choice. We look at longer types of calculation questions. And don't miss out on the teacher tips that I give throughout all these questions. So let's start off with a multiple choice question. So as you can see, I copied and pasted these from past papers. So this one says, red light of frequency F and wavelength lambda. So that's the frequency, that's the lambda. Lambda's wavelength. It's just the name for that symbol. Shines on an object. The red light is then replaced by a light of a higher energy. How does the frequency and wavelength of the light shining on the object now compare with that of red light? So what's important to note about multiple choice questions is that they like to test you on your knowledge of relationships. So what they're testing you here is they say that they are replacing the light with a light of higher energy. And they want to know if you understand how energy relates to frequency and how energy relates to wavelength. So we need to look at our formulas in order to help us with this. The first formula that will be useful for us in order to determine the relationships is this one over here. So that is E, energy, is equal to Planck's constant times frequency. And from this formula, you should understand that frequency and energy are directly proportional. You may have seen your teacher write it like that. That means directly proportional if H is constant, and it always is. So that means direct proportional. You should know what that means. It means that if frequency goes up, energy goes up. Or if energy goes up, frequency goes up. Or if frequency goes down, energy goes down. So they do the same thing. So if you look at our question, they replace the light with a higher energy. So what did energy do? Energy of the light went up. Because energy of the light went up, because frequency and energy are directly proportional. What that means actually is that if energy went up, it means that frequency had to have gone up as well. So we will select out of A, B, C, or D. We already know that the frequency must be greater than the original frequency. So greater than F. So we either on option A or option C at the moment. We can immediately already eliminate option B and option D because the frequency does not stay the same. If the energy increased, it means that frequency increased or is greater than. So it's either A or C. How do I figure out the last one? Well, they want to know about wavelength. There's two ways that we can decide on this. So if you look at your formula sheet, we could use this formula over here. That formula says E is equal to HC over lambda. Now, if you watch my previous video on electromagnetic radiation, you will know that H and C, that means Planck's constant H, multiplied by the speed of light C. And there's wavelength. Now, what you need to understand about this relationship is that because wavelength is under the fraction, we are dividing by wavelength. What it means is that energy and wavelength are inversely proportional. Now, what does inversely proportional mean? It means that if one goes up, the other one goes down. So if energy went up, it means that wavelength must have gone down, which means that our answer is C. C is our answer because remember, the frequency is greater than, energy went up, so frequency went up because those are directly proportional, and the wavelength went down because if energy goes up, wavelength goes down because they are inversely proportional, which means they do opposite things. Another formula that we could have used to figure that out is this formula over here. And this formula shows you that frequency and wavelength are also inversely proportional if the speed of light is constant. So this is the speed of light and it's constant. It will always be 3 times 10 to the 8. So what this means is that if frequency goes up, wavelength must go down. They must do the opposite stuff. They're inversely proportional. So I don't mind how you get to your answer, but we know that F went up. So that means wavelength must have gone down, less than. That means our option is C. Right, let's jump into an actual question. Our first question says, how are electromagnetic waves generated? This is a theory question. And the answer to this question is accelerating charges. You need to know this type of theory question. So there it is, accelerating charges. It's just 1 mark. But just to quickly recap theory, remember, electric charges accelerate. And that causes a magnetic field. And the magnetic field produces an electric field at a plane of right angles to it. And the electric field produces a magnetic field, and the magnetic field produces an electric field. And remember, they occur at 90 degrees or right angles to one another. And that is how it happens. So all that you need to say is accelerating charges, but just know that it is the electric charges that accelerate that produces a magnetic field. The magnetic field recreates an electric field and so on. And those fields are at 90 degrees to one another. Right. Theory question done. Our next question is, what type of electromagnetic radiation has the highest energy? Now, you need to remember that for electromagnetic radiation, energy of the electromagnetic radiation or the photons is calculated by multiplying the constant, Planck's constant, by the frequency. And you should know that energy is directly proportional to frequency if H is constant. And what that means, grade 10s, directly proportional means that if frequency goes up, energy goes up by the same proportion. So if frequency doubles, energy doubles. If frequency halves, energy halves, and so on. So to find out which of the radiation has the highest energy, I need to look for the ones with the highest frequency. That's it. So you look on the table. Here's your table. This is frequency. You look for which one has the highest frequency, and that is clearly gamma rays. You should know that anyway. Gamma rays have the highest frequency, therefore they have the highest energy. And that will be your answer to 8.3. Explain the answer to the question. So I'll write that out for you now. But just take note here, 10 to the power 5 to 10 to the power of 10. So to the power of 5, I hope you know what, for example, 10 to the power of 2 means. It means 10 times 10, which is 100. 10 to the power of 3 is 10 times 10 times 10, so it's 1,000. So 10 to the power of 5, that thing will have 5 zeros. 10 to the power of 10, it'll have 10 zeros, and so on. So here you can see gamma rays as 10 to the power of 18 and 10 to the power of 21. That's very big numbers. Gamma rays, highest frequency, highest energy. That's why it's the most dangerous type of electromagnetic radiation. Okay, so how do you answer 8.3? So here's our answer for 8.3. Explain the question. So it has the highest frequency. That's enough. Or energy is directly proportional to frequency, or you can say E is directly proportional to F, just like I wrote it over there. Okay, so that is what I would do. I personally, because it's 2 marks and they want us to explain the answer, I would say it has the highest frequency. Okay, so it has the highest frequency and energy is directly proportional to frequency. So what you're telling me is, well, gamma rays has the highest frequency, and because they're directly proportional, that means it will obviously have the highest energy. So I would include both of these points. You can either write out energy as directly proportional to frequency, or you can write it like that. Our next question says, a certain type of electromagnetic radiation has a wavelength. You know the symbol for wavelength is that? Of 600 times 10 to the minus 10 meters. It must be in meters, so that's all good. And then they say identify the type of electromagnetic radiation by performing a calculation. Now, grade 10s, we don't expect you to memorize the different wavelengths and the different frequencies of each type of electromagnetic radiation. We will have to give you a table like this. So they give me a table which contains ranges for the different frequencies. So if you are infrared, you'll have frequencies within this range. Now, what I want you to understand is that 10 to the 18, 10 to the 21, that would be the last part of your range. So for example, if I had to do 3 times 10 to the power of 8, what type of radiation would that be? 10 to the power of 8, that would fall in here. So that would be a radio wave. I hope that makes sense. If it is 1 times 10 to the power 14, that would be infrared, or it would actually be on the border between infrared and visible light, because check, they both have times 10 to the power 14. Okay, so basically what we need to do is we need to use the wavelength that they gave us. They gave us wavelength, and we need to calculate a frequency. Then we're going to compare those frequencies to the frequencies in this table over here and choose which radiation we think it is. So how do you convert, or how do you calculate frequency if you have wavelength? So I hope you remember your formula sheet. So I have wavelength and I want frequency, and we know all types of electromagnetic radiation travels at the same speed, which is the speed of light. So I'm going to use this formula because I know C, I know wavelength, I can get frequency. So you need to write your blank formula first. That'll get you a mark. Then you must substitute in your values. So we know C is 3 times 10 to the power of 8. Frequency is what we're looking for. The wavelength is 600 times 10 to the power of negative 10. And we need to solve for frequency. So please solve properly. We are multiplying by frequency over here. So when we take this over, we need to do the inverse operation, which is divide. So we say 3 times 10 to the power of 8 divided by 600 times 10 to the power of negative 10. So do that on your calculator quickly. And we get 5 times 10 to the power of 15 hertz. So this is where you get your marks. You get a formula mark, then you get a substitution mark, you get an answer mark, but then you must still identify the type of electromagnetic radiation. So we go back to our table, we look at our values. We have 5 times 10 to the power of 15. So at this end of the scale, this would be just reaching 1 times 10 to the power of 15. So 5 times 10 to the power of 15 will be between these two values over here. So therefore, our light is ultraviolet light. And that would get you your 4th mark. State one application of the type of radiation identified in question 8.4.1. Now, the different applications and uses of the different types of radiations is something that you must study. It is theory work. I went over it in my previous video, which will be linked in the Waves playlist in the description box below. But these are our acceptable answers according to the memo. So I would probably go with sterilization of medical equipment or something like that. That is what I have in my notes. So that's what I would go with. But any of these would be acceptable because we're talking about UV radiation. Our next question is a multiple choice question. So it says, which one of the combinations below is the correct order of electromagnetic waves in increasing wavelengths? So remember, we got a spectrum. On one side of the spectrum, we have high frequency, okay, which is also high energy. Remember, high frequency means you have a high energy because those are directly proportional. If you have a high frequency, you have a small or short or whatever wavelength. Okay, high frequency, short wavelength. Big F, small wavelength. On the other end of the frequency, other end of the spectrum, we have a low frequency, but we have a big or large or long wavelength. Okay, so they want to know which one of the following combinations is correct for increasing wavelength. So in other words, we must end off with the thing that has the biggest wavelength. So I hope that you know your order, but I did go through the order in the previous video. Here's a quick reminder. So here's the order of the electromagnetic spectrum. Gamma rays is on the one end of the spectrum. That has the highest frequency, highest energy, shortest wavelengths. On the other end of the spectrum are radio waves and microwaves. Radio waves have the lowest frequency, but the biggest wavelength. Think about the wavelength being very big. It travels over long distances, a radio wave. Okay, so let's look at our options once more. So we need something where we have either radio waves or microwaves at the end because those are the biggest. So, for example, this one won't make sense because here microwaves are, this is the other way around. So they say increasing wavelength. So in other words, that wavelengths must be getting bigger and bigger. So B is definitely not correct. And if you struggle to remember the order, you can use one of these acronyms like raging Martians invaded Venus using X-ray guns. So R is radio waves, M is microwaves, and so on. So our correct answer is A. C is incorrect because they say microwaves have longer wavelengths than radio waves, and that's not true. Radio waves should be at the end. And I know you're probably thinking, oh, but here radio waves isn't at the end, but radio waves isn't included at all in this one. So it's not C. And the reason why D is incorrect is because they swapped out some of the lights here. So it should go gamma rays, X-rays, then ultraviolet. But this one goes gamma rays, X-rays, and then visible light. So it's wrong. So our correct answer is A. By process of elimination, you can get to the correct answer. Right. Our next question. Consider a laser pointer and a cell phone as shown below. State the type of electromagnetic radiation that is emitted by the laser pointer. So again, this is theory questions that you can memorize, you can study. And that is, for a laser pointer, it is infrared radiation, which has quite a high frequency and therefore a high energy, which is why you shouldn't shine lasers in people's eyes. Okay. Cell phones. What do you think about cell phones? Cell phones are used for communication, and that takes place through our radio waves. However, the memo also accepts microwaves, but it's very low energy waves. So low frequency, low energy, therefore not dangerous. Okay, a laser pointer uses red light photons. So photons, remember, are packets or pockets of energy within electromagnetic radiation, within light. And these red light photons have a wavelength of 620 nanometers. Immediately your brain should be going, uh-oh, nanometers, I need to convert this to meters. But before we do that, before we jump into our calculation, let's define the term photon. This pops up often in your exams. A photon is a packet of energy found in light. That's your definition. You get 2 marks or you get nothing. You have to say packet of energy. You have to say found in light. It says calculate the energy of a red light photon. Now remember in the previous question, they gave us this, which is wavelength. So we know the wavelength. Great. We know it's 620 nanometers. They want energy, so they want E. This is 6 marks. So how do we do that? If we look at our formulas, we are looking for energy and we have wavelength. So which formula do you guys think makes the most sense to use? Well, I know some of my students want to go for this formula, which isn't wrong. That's fine. You can most definitely do that. If you go for that formula, you're looking for energy. Planck's constant, we know that. It's given on our formula sheet over here. So we have that. And then you're like, oh, wait. No, I don't have frequency. So if you want to go this method of using this formula, that's okay. But then we first need to use this formula in order to find frequency. Can I use that formula in order to find frequency? Yes, I can. Because I know C, the speed of light, it's given here on your formula sheet. I can work out frequency and I know the wavelength. Once I have frequency, I can put it in here and then we can get energy. We can either do that way or we can just do this way where I use this formula. So if I have the wavelength, which I do, and I'm looking for energy, this is the quickest way to do it because H and C, those are both constants given in our table. So I'm going to use this one because it gets us the answer in one go. So you write your formula first, and that is where you get your first mark. I know this question is worth quite a lot of marks. The reason why is because the memo gives an option of doing it this way, where you first work out frequency using this formula. And then once you have frequency, you substitute it into this formula. So once you get frequency, you put it in there, and then you use this formula to work out energy. So it's a lot easier to give 6 marks when you do it 2 ways like that. However, you are allowed to do it like this, and the memo does allocate marks for doing it like this. It's just you get a lot of substitution marks. So H is Planck's constant at 6,63 times 10 to the negative 34. Please read those carefully off of your formula sheet. C is 3 times 10 to the power of 8. They squash together, so it means times. Wavelength is 620 nanometers. How do you convert that to meters? It's 620 times 10 to the power of negative 9. Nano, 9. Okay, you have to do the conversion properly. 620 times 10 to the negative 9. And then you calculate your energy. You type it in exactly like that in your calculator. You use brackets. And I get 3,06 times 10 to the negative 19. Don't forget to write that part in. And because we're working out energy, our unit is joules. Okay, so 6 marks is quite a lot for this question, I'm not going to lie. You'll get an answer mark. You will get a formula mark. So that's 1, 2, 3, 4, 5. And then actually what the memo does is they give you another formula mark here. That's quite a lot. Usually this question could be worth maybe 3 or 4 marks. It's not very often that we make it worth 6 marks. It's generally formula, substitution, answer, and if we're being nice, we can do top and bottom substitution. Okay, refer to the answer to question 8.2.2 and explain why it's dangerous to shine a laser pointer in a person's eye. So your answer for 8.2.3 is that lasers have a high energy and intensity, and therefore it can penetrate the skin tissues and it can cause harm, it can cause damage. There we go. If you'd like to see more past paper questions like the one on the screen, please let me know. I can do many more videos like this. I have more videos like this in my playlist, as a matter of fact. So check out the links in the description box below, and don't forget to subscribe for more physics. Bye everybody.